All right, let's get into it. Today, we're talking about how industrial machines are learning to speak. And no, I don't mean the usual clanks and whirs. I'm talking about a whole new kind of communication. One where a machine can basically raise its hand and tell you it's not feeling well long before it ever actually breaks down.
I mean, just think about that for a second. What if some critical piece of equipment, on a car assembly line or inside a huge power plant, could just send you a little ping that says, hey, just a heads up, I'm probably going to need some maintenance in about 48 hours. This isn't some far-off sci-fi idea. It's what's happening right now, and we're going to unpack exactly how.
Because, in the industrial world, silence is definitely not always golden. A tiny little change that you couldn't possibly see or hear, a slight bump in temperature, a little shift in vibration, that can be the quiet start to a massive, expensive failure that just brings the whole operation to a dead stop.
So, how in the world do you listen for these silent warnings? Well, the solution is all about following the data. So for this explainer, we're going to trace the path of one single digital signal, from the moment it's born as a physical event, all the way to its transformation into an alert that can literally save millions of dollars. Let's see how that journey kicks off. Okay, so our journey starts right at the source. This is where the physical world of things like heat, pressure, and motion gets translated into the language of computers, which is, of course, data. So it all starts with a sensor grabbing some kind of raw measurement. That data then flows to a local edge gateway, which is kind of like the neighborhood post office, right? It just collects all the local signals. From there, it gets sent over a specialized network and then into a processing engine, which polishes it all up and gets it ready for the real magic to happen.
Now here's something that is absolutely crucial: time synchronization. Imagine you're trying to figure out a problem by listening to 10 different people, but they all start their story at a different time. It would be total chaos. By stamping every single piece of data with a super accurate time, we're talking sub-millisecond here, engineers can line up all the events perfectly and see the complete picture of what's really going on with that machine.
Okay, so once all our data is captured and perfectly organized, it's time for the next big phase, actually finding that one critical warning sign that's hiding in a huge sea of normal, boring noise. And this is where AI comes into play.
You see, a running machine is just constantly generating data. And most of it, like 99% of it, is just the sound of it doing its job normally. So the first thing any AI has to do is learn what normal sounds and feels like so it can filter all of that out. That way, only the weird, unusual signals are left. It's really like trying to hear a single whisper in a packed, noisy stadium.
And to do this, data scientists use some incredibly clever tools. You've got AI models that basically become experts on a machine's normal rhythm, so they can spot anything that deviates from that baseline. Then you have other models that are specialists. Maybe they just listen for tiny fleeting blips in vibration or sound. You can really think of it as a whole team of digital experts, and each one is trained to spot the most subtle signs of trouble.
But here's a really interesting problem. A real paradox. To teach an AI what a machine failure looks like, you need a ton of data from actual failures. The catch is, the whole point of this system is to prevent failures from ever happening. So that data is incredibly rare. So, how do you solve that?
Well, the solution is just brilliantly counterintuitive. It turns out, to get really, really good at spotting a forgery, you don't just study the real thing. You also study the best fakes.
And this idea is behind something called a generative adversarial network, or GAN. It's so cool. You have two AIs basically fighting each other. One is a forger that gets really good at creating realistic but totally fake failure data. The other is a detective that tries to tell the fake data from the real data. They compete against each other, and in the process, they both become masters at their job. This gives us a massive library of failure data to train on without ever needing a machine to actually break down. Genius, right?
So now we've got a smart AI model that's been trained to spot trouble. But where does this model actually live? Should it be on some distant cloud server, or should it be right there, next to the machine itself? This brings us to a really critical decision: cloud versus edge computing. For a lot of things we do, the cloud is totally fine. But when a machine needs to react instantly to prevent a disaster, sending data hundreds of miles away to a server and then waiting for a response, that's just way too slow. Edge computing puts the AI's brain right there on the factory floor. This gives it near-instant reflexes and, get this, the ability to work even if the internet connection goes down. And the impact here is massive. Just look at this number. For a really time-sensitive job, like predicting wind energy to adjust a turbine blade, moving the processing to the edge can cut that delay, that reaction time, by up to 65%. That's easily the difference between a small automatic adjustment and a major problem.
But really, it's not just about being faster. It's about building a system that's resilient, that's self-sufficient. With edge computing, the factory's brain is local. It can keep running intelligently and safely, making its own smart decisions without having to constantly rely on a connection to the outside world.
So, we've got the data, we've got the super smart analysis, but there's one last absolutely crucial piece to this puzzle, translating all of this high-tech insight into a simple action for a human operator.
This is it. This is the finish line for our little piece of data. After this whole journey, it's been transformed from just a raw number into a clear, understandable warning that pops up on a screen right in front of the one person who can actually do something about it.
And this translation part is so important. A complex technical measurement like a reconstruction error becomes a simple alert, early warning, abnormal vibration. A raw anomaly score becomes a direct, actionable instruction, maintenance required in 48 hours. The AI doesn't just find the problem, it speaks our language.
Now, for this entire system to actually work, for an operator to make the call to shut down a production line based on what a computer is telling them, there has to be absolute, rock-solid trust in the data and the AI behind it.
And that trust doesn't just happen. It's earned through really careful work. It means constantly checking to make sure the data is good, running automated quality checks, and retraining the AI models so they stay sharp. And it's also about finding that perfect balance. You want this system to be sensitive enough to catch real problems, but not so sensitive that it's constantly crying wolf and creating false alarms. So here's the bottom line. The ultimate goal isn't just to find problems. It's to find them early enough to give a human operator the most valuable resource there is, time. Time to plan, time to schedule maintenance, and time to act before a little problem becomes a catastrophe. And with that, our data's journey is complete. We've followed it from a tiny, invisible sensor reading, through all that complex AI analysis, all the way to a clear alert that helps a person make a better, smarter decision. This is how we are finally, truly giving a voice to our machines.
And this really leaves us with one last fascinating question to think about. We've taught our machines to warn us about their own health. As this technology gets better and better, and every single bolt and gear in a factory has a voice, what other secrets are they going to be able to tell us?